How did people survive summer before air conditioning existed? My name is Pico. This question has been bothering me for a while. Someone solved this long before electricity existed. Let's find out. Step outside in Yazd in July. The air is dry, the sun is flat and total. The temperature is pushing 45 degrees, and there is nowhere to hide from it, except inside. Inside, it's cool. Not cold, but cool. Cool enough to breathe, cool enough to sleep, cool enough that a city of people has lived here through summers like this for more than 1,000 years. Without a single machine. There is a tower above me, tall, narrow, open at the top. It has stood here for several hundred years. It has no moving parts. It uses no power. It does not pump anything, compress anything, or consume anything. And the room below it is cool. I want to know how it works. But more than that, I want to know who figured it out first. What they understood about heat and air and earth, and what we forgot when a machine began doing the work for us. Summer in the ancient world was not an inconvenience. It was a threat. In the river valleys of Mesopotamia, modern Iraq, summer could climb past 45 degrees, and in the south, heat like this was not rare. In Egypt, hot desert winds could arrive in spring, carrying dust and heat across the country. In the Indus Valley, in Persia, in the Mediterranean basin, heat was the condition everything else had to be built around. There was no escape from it. Not really. You could move slower. You could rest at midday. You could soak cloth in water and drape it across a doorway. But the heat came through the walls, through the roof, through the ground itself. By afternoon, the inside of a mud brick house was nearly as hot as the outside. And people died. Not dramatically, not all at once, but steadily. The elderly, the very young, anyone whose body had stopped being able to regulate itself. Heat was one of the oldest killers in the ancient world. This was just summer. The question wasn't how to make it comfortable. The question was how to survive it. How to keep food from spoiling in a day. How to keep the sick from getting sicker. How to sleep when the air itself felt like something pressing down on you. People tried everything. They moved their sleeping mats to rooftops at night, where the air moved. They built thick walls, not for decoration, but because a thick wall gave heat somewhere to go first. It slowed the day down before the temperature reached the room. They dug down. Underground was always cooler, caves, cellars, sleeping pits carved into rock. The earth itself was a buffer, but you can't live underground, and rooftop sleeping only works at night. There had to be something else. Something that worked during the day, inside, without requiring you to move somewhere else entirely. The first answer wasn't a building, it was a direction. Down. Across hot regions, people kept discovering the same basic truth. That a few meters below the surface, the Earth changes temperature much more slowly than the air above it. In hot, dry regions that made underground rooms dramatically cooler than the surface during the worst hours of summer. People had known this long before anyone built a structure around it. Farmers knew it. They stored grain underground not just to hide it, but because the temperature stayed stable. In Iran's hot, dry cities, traditional houses often use deep basement rooms for the hottest parts of summer. In some regions, the entire midday household moved below ground. The upper floors were for morning and evening. The lower rooms were for the hours when staying above ground meant suffering. The earth was doing something specific. It was absorbing heat slowly, storing it, and releasing it slowly. Smoothing out the violence of the day's temperature swings. A room carved 2 meters into the ground didn't get the full force of a 45-degree afternoon. It got yesterday's temperature, or the day before's. The earth was always running behind the sun, but the deeper you went, the harder it was to live there. Underground rooms were dark, the air was still. Without ventilation, they became oppressive in a different way. Not hot, but airless. A family could sleep there, could rest there for a few hours, but they couldn't cook, couldn't work, couldn't do much of anything. And then someone noticed something about the air above. In the desert, wind was not constant, but when it came, even a dry, hot desert wind, it moved, it carried. And if you could take that movement and direct it, shape it, pull it through a space and down into the earth, you could combine both things. The coolness below, the movement above. That was the idea. Simple enough to state in one sentence. Hard enough to build that it took centuries to refine. The badgir was not invented all at once. It was figured out slowly by builders who understood that air behaves almost like water. It flows, it finds gaps, it responds to pressure, temperature, height, and shade. Warm air rises, moving air pulls, and if you give air a channel, it will follow the path you build for it. In Yazd, the towers are still standing. Some were built to catch the wind directly. Others could work almost in reverse, using suction, shade, and rising hot air to pull stale air out of the rooms below. The builder had to understand the wind before he laid the first brick. Which direction did it come from in July? Which face of the tower would be in shadow by afternoon? Where did the air naturally want to go? These were not engineering questions, they were observation questions. The tower pulled air down. But pulled it into what? Below the house running beneath the city were the qanats, ancient underground water channels that drew water from underground sources and carried it into desert towns. Some badgir towers were positioned directly above these channels. The air coming down the tower passed over the cool water in the qanat. It dropped in temperature. Then it rose, slightly cooled, slightly humidified, into the rooms of the house. No pump, no compressor, no moving parts of any kind. The system ran on the difference between the air at the top of the tower and the air at the bottom of the house. A difference in temperature, in pressure, in the basic tendency of hot air to rise and cool air to sink. The builder didn't fight those tendencies. He used them. They didn't fight the heat. They moved around it. A house in Yazd with a working badgir, thick earthen walls, shaded courtyards, underground rooms, and sometimes qanat water could feel dramatically cooler than the air outside. The rooms below ground were the coolest. The rooms at ground level were bearable. The upper floors were for storage during summer, left to the heat because the heat had to go somewhere. The whole house was organized around where the air wanted to be. Wealthy families built taller towers. More height meant more pressure difference. Stronger airflow, more cooling. The height of your badgir was a signal of means. But the principle was the same for every house that had one. Air comes in at the top, moves down through the channel, crosses the cool earth or the qanat water, rises back through the living space, exits, a continuous, silent, invisible engine, running on nothing but the difference between here and there. Yazd was not alone. The same logic, move air, use shade, go underground, let the earth do the work, appeared across many hot regions that had to solve summer without a machine. In Egypt, wind-catching devices go back to ancient architecture and later became known as the malqaf. They worked on the same principle as the badgir, a tower open to the prevailing wind, channeling air down into rooms below. Egyptian houses used wet reed screens hung across doorways so that the moving air passed through damp fibre and arrived cooler on the other side. Evaporation as a tool, not an accident. In India, stepwells were not just water sources. The great stepwells, like Rani Ki Vav in Gujarat, descended through 7 levels of stairs and sculptural galleries. In medieval India, stepwells could become summer refuges. People gathered there not just to draw water, but to sit in the cool air that collected at the bottom. sheltered from the sun by the stone walls rising on every side. In Rome, thick masonry, shaded courtyards, porticos, gardens, and water features helped buffer the heat. The courtyard let light in while controlling direct sun. Stones slowed the day down, water added moisture to the air. The building itself resisted the heat before the people inside had to. Different materials, different places, different centuries. The same underlying insight. You cannot cool air by fighting it. You cool it by moving it somewhere cooler, passing it over water, putting stone and earth between it and the sun, and letting physics do what physics does. My friend, this was not a collection of tricks. This was a body of knowledge, accumulated over generations, tested by summers that had real consequences. If you got it wrong, people suffered. If you got it right, a city survived. And it worked. For thousands of years it worked, until it didn't need to anymore. In 1902, a 25-year-old engineer named Willis Carrier designed a system to control humidity in a printing plant in Brooklyn. The ink was bleeding. The paper was warping in the summer heat. The problem wasn't comfort, it was production. Carrier's solution pumped cooled, dehumidified air through the building. It worked. Over the next 2 decades, the same principle moved from factories into movie theaters, department stores, and office buildings. Not for survival, for comfort, for commerce. The machine spread fast. Faster than passive systems could, because it asked less from the building itself. No careful reading of wind direction, no deep relationship with the site, no knowledge of where water moved underground. You installed it. You turned it on. The towers in Yazd are still standing. Many are now heritage more than infrastructure. The qanat system remains part of the city's story, but the buildings that replaced the old ones were not designed around air. They were designed around the assumption that a machine would handle it. The knowledge didn't disappear. It just stopped being necessary. Most modern cities no longer build around wind. I am still in Yazd. The tower above me hasn't moved. The promise inside it is still clear. Air can be shaped. Somewhere below the city, qanat water has moved through the earth for centuries. Slow, hidden, patient. I didn't find a lost secret. I found something that was never hidden. Just replaced. A body of knowledge that worked for thousands of years, quietly, without electricity, without a compressor, without anyone needing to understand it, except the people who built it. The machine is easier, I understand that. But I keep thinking about the builder, the one who had to read the wind before laying the first brick. What everyday object do you want Pico to follow next? Tell me below.